Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on partial differential equations. And in particular we're going to look at an idea known as Green's first identity. Now this identity is one of several identities due to the famous mathematician and physicist George Green. Now our interest in this particular identity is related to partial differential equations, and in particular on proving, say, uniqueness or non-multiplicity of solutions to boundary value problems involving Laplace's equation or Poisson's equation. Now the application of Green's first identity in that context will be looked at in other videos. So in this presentation I'm going to basically state Green's first identity and provide a simple proof. Okay, so the basic identity is here. Now suppose you have, we're just working in the plane by the way here, so the xy plane, just to keep it simple, but the idea is generalized to n dimensions. Okay, suppose you've got a two-dimensional region D, and you've got functions k and h being functions of two variables that are defined on this set and its boundary, and suppose that the boundary is a so-called piecewise smooth curve and it's closed. So for example, a simple shape, think of the boundary of a filled rectangle. That would satisfy these conditions. Suppose k and h are continuous and have continuous first and second order partial derivatives. If all those conditions are satisfied, then the following identity holds. This line integral, so you're integrating around the boundary of D, is equal to this double integral over the whole two-dimensional region D. Okay, now let me just sort of talk a little bit more about what the notation here is about. Okay, this sort of nabla h is the gradient of h. Okay, so sometimes called the grad h or the gradient of h. So this is a vector field whereby you take the partial derivatives of h and you write them as a vector. Okay, so I and j are the standard unit vectors. The subscripts mean partial derivatives. Okay, the dots mean the dot product. The n vector here is a unit vector that is so-called normal to the boundary, and it's outward pointing. So it doesn't point to the inwardly, it points sort of the opposite way. The nabla squared here is the Laplacian operator. Okay, so basically the Laplacian operator is just the following. It's, now I just need to sort of squeeze this in here. You take the gradient of a h to form this, and then you take the divergence. Okay, now let me just, I haven't really put much room in there, so let me sort of just go down and explain that a little bit better. So this sort of nabla dot is the divergence, right? So if you actually compute that, it's just the sum of the second order non-mixed partial derivatives. Okay. I think that's everything here. Oh, actually, one more thing. This sort of partial derivative notation, the dhdn, is sometimes called the external or normal derivative. And it's just this part here, okay? So it's the component of grad h in the direction normal to the set D. Okay, so that's Green's first identity. The big picture with Green's first identity is the following. It's a fundamental theorem of vector calculus. Okay, now you see that, you know, the divergence and the gradient and the Laplacian in a course in vector calculus, our third course in calculus. But the big picture here is that basically here you're integrating certain things over the whole set, and on the left-hand side you're just integrating over the boundary. So it tells you that under certain conditions you can integrate certain things not over the whole set, but just integrate over the boundary of the set. And this is what a fundamental theorem of calculus does. Okay, it relates some sort of integral over a higher dimensional set with some sort of integral over the boundary of that set. Okay, so let's prove it. Oh, actually one more thing. This kind of identity can also be thought of as sort of like an integration by parts formula for vector calculus. So if you sort of take this over to the other side and maybe take this over to the other side, it's actually, you can draw comparisons between that and the regular integration by parts that you see in a first course in calculus. Okay? All right, well, how do we prove it? Well, we use the so-called Gauss-Green, or the Green-Gauss divergence theorem. So here we're just working in the plane. Okay, and then of course this is also a fundamental theorem of calculus because you're integrating over some, say, two-dimensional set, and then over here you're just integrating over the boundary. Okay, now the proof is actually pretty easy. If you compare this with this, how can I make this thing be the f, the vector field f? Well, just choose f to be this product. Now remember, k is a scalar valued function, grad h is a vector valued function. So this product will be a vector field, or a vector field. Okay, so let's call this star, and we're going to let the vector field be the following product. And on the left-hand side, we're going to obtain that, so that's great. So all we want to do is compute that, and hopefully we end up with this right-hand side. Okay. Okay, so all right. So let's replace f with that. Okay, so this, remember, is the divergence of what's in here. So how can I, and this is a product, so how can I take the divergence of a product? Well, there is a product rule. If you think of divergence as some sort of, roughly speaking, derivative, you can take the divergence. You can expand this in the following way. Okay, so let's apply the divergence to the gradient of h. So if you take the divergence of the gradient, you get the Laplacian. So it's k times that. Plus the divergence of k times the gradient of k. So what's that? That is just basically the gradient of k times the gradient of h. Okay, that's how we frame it in this context. Okay, so that then goes to the Laplacian, and we get exactly what we wanted. D8, where we used the product rule for the divergence. Okay, so it's pretty easy. The proof is pretty easy. Okay, so just to summarise, Green's first identity is one of at least three famous identities due to the mathematician and physicist George Green. We're interested in this particular identity because of its applicability to Laplace and Poisson type PDEs together with some boundary conditions. And in particular, in other videos, we'll look at how to apply that to ensure the boundary value problems have at most one solution. You can think of Green's first identity as some sort of integration by parts type fundamental theorem of vector calculus. The proof, at least in the plane, is pretty easy. You apply Gauss's divergence theorem for a particular vector field F. Now, because Gauss's theorem generalizes to n dimensions, so does Green's first identity. So you can prove 3 dimensions, 4 dimensions, n dimensions. So in forthcoming videos, we will look at the applications of Green's first identity to PDE. I hope you can join me for those presentations.